Okay, good morning, everyone. Thank you for taking the time of hearing me, and thanks to the organizers for giving me the opportunity of present some of my work here. My name is Agustin Silva, and today I'm going to tell you how we test the cosmological principle in a quantum universe that emerges out of a non-perturbative path integral for quantum gravity, that of causal dynamical triangulations. This talk is based in this paper here that we published recently with Renate Law, the previous speaker, and also my PhD supervisor. Okay. So let's start with the outline of the talk. So first, I'm going to briefly review what Renate told you about what causal dynamical triangulations is. And also, I'm going to describe how these causal dynamical triangulations provides an emergent universe that is zeta-like, as Renate mentioned. And we would like to study the properties of this emergent universe, and this is why we are going to construct during this talk quantum observables that are capable of measuring homogeneity and isotropy of this quantum universe. So if I have time, I will introduce you of how we build isotropy observables, but most of the talk would be dedicated on how we build homogeneity observables. And then, of course, at the end, I will just state the conclusions in the forthcomings. So briefly, again, I didn't know that Renate's talk was going to be so useful for me, so thank you. Causal dynamical triangulations is a non-perturbative approach to quantized gravity that basically regularizes the gravitational path integral by replacing this sum over all possible metrics with a sum over all possible simplicial discretizations of spacetime. And it has a very beautiful feature that when one goes from the continuum to the simplicial manifolds, the Einstein-Hilbert action is discretized in a very simple manner that only depends on the number of building blocks that one uses to discretize spacetime. The number of four-dimensional building blocks and the number of vertices that one uses in this discretization. And of course, in some parameters that depend on the cosmological constant and the Newton coupling. Now, this simple action has a counterpart, which is that, as Renate said, we don't have tensor calculus. And if we want to study spacetime, we only rely on two tools, measuring distances and measuring volumes, which is a very challenging thing because one wants to study curvature, one wants to study, geometrical properties, but only using distances and volumes. So as I said, there is no hope of using tensor calculus because the path integral configurations that appear in this approach, they look like this. They are very non-smooth and fractal, and there is basically no hope of applying differential calculus. So as I said again, and I want to reinforce this, is we only know how to measure distances and volumes. And why do we want to study these spacetimes? Well, because there is a beautiful property of this theory that in its parameter space, there is a region called the zeta phase, where all these very non-trivial geometries, they conspire to give rise to an emergent universe that has the beautiful property that its spatial volume as a function of the proper time fits perfectly a cosine cube law. Now, as Renate said, this is a zeta-like universe that comes out of the path integral without no symmetry assumptions. And we want to construct observables capable of testing the symmetries of this emergent spacetime. We want to study the properties. Why? Well, because we would like to, using this emergent, the zeta-like universe, we would like to somehow justify the usual assumed initial condition of the universe as a isotropic and homogeneous exponentially expanding universe. And this raises a natural question. Does this emergent universe satisfy the bounds in inhomogenities and anisotropies for inflation to happen? Okay, if we want to answer this question, we need to develop quantum gravitational observables capable of measuring homogeneity and isotropy, only using distances and volumes. So this is going to be a bit challenging, so let's start from the beginning of what homogeneity is. So a homogeneous space is a space that has translation symmetry of all its properties. Now, this definition is a bit challenging because it has some difficulties. at least in this approach, because we do not have a group action or a translation symmetry. We don't have tensor calculus. And also this definition is a bit restrictive because in physics, symmetries usually appear at a certain scale, like homogeneity. So we would take a more statistical point of view, and we will take a definition of homogeneity as a space that looks the same everywhere at a given scale. I will formalize that later. And we will define observables capable of testing this symmetry at different scales. So we take ideas from astronomy, where people, if one wants to know if space-time is homogeneous, people just takes a chunk of the universe, which can be this box here, and it picks a property, for example, the temperature of this chunk of the universe or the density of matter, when averages this property in this chunk of the universe and compares this chunk of the universe with other chunks. And basically, one states that the universe is homogeneous if all these chunks have the same average property. So if the average temperature here is the same as here and here and here, then one concludes that the spacetime is homogeneous. And this is the viewpoint that we would take in these quantum spacetimes. But this introduces two things: a scale. For example, in astronomy, the universe only looks homogeneous above 300 megaparsecs, not below. So this is a symmetry that appears at a certain scale. And also, it introduces a way of comparing different chunks of the universe. So we want to do this, but in a covariant way, without using coordinates. So in our observables, our chunks of the universe are going to be geodesic spheres. This only requires the notion of a distance. So we know how to measure distances in this space-time, so we would take a distance equal to delta, and we will construct a sphere around a given point in space-time. So these are going to be our chunks of the universe, analog to these boxes that I draw. Now, in flat space-time, before that, we will also pick a property that we will call Q, and we will study the homogeneity of this property in space-time. And what we will do is to average this property that depends on a point, a scalar property. We will average this property over geodesic balls, and this will give us a coarse grain property, a coarse grain quantity of spacetime. In flat spacetime, this way of coarse graining basically eliminates momentum modes of energy higher than 1 over the inverse of 1 over the distance scale. Here in a curved background, we do not have a momentum space, but perhaps this helps for some people to understand what we are doing. So, introducing some notation, we will first pick a property, as I said, called Q. At a point X and at a distance scale delta, we'll define a geodesic ball as B of X and delta, and its volume. This is just a continuum notation, but this is also well defined in these quantum geometries. And we will define the coarse grain quantity, which is the average of this quantity all around this geodesic sphere, as Q of X delta, which is nothing more than just the average of Q inside this geodesic sphere. Okay, great. So now we have a way of coarse graining a quantity, which was the same as I said in astronomy they just average, for example, the temperature of the universe in a given region. Well, this is exactly the same. We are averaging a property in a given region of space-time determined by these geodesic balls. How do we measure if space-time is homogeneous? What we do is, without using translation, right? What we do is we look at the standard deviation of this property all across the manifold. So this standard deviation of this property Q of this coarse grain property Q at a scale delta is just the square root of the integral of the deviation of this coarse grain property minus its average all over the manifold. So Q bar delta is just the average of this coarse grain property all over the manifold, and this is our reference value. So we should study deviations from this reference value. And if one takes the quotient between this standard deviation with the absolute value of the mean value of this property, one has a quantity that determines percentual deviations from perfect homogeneity. Now, this quantity is an observable because it's just a point-independent scalar that we can just introduce into the path integral. Now, this point-independent scalar is scale-dependent, so this tests homogeneity at different scales. So each delta here is a scale at which we are proving the homogeneity of space-time. And if, for example, if this observable is equal to 0, then that means that the coarse grain property at this scale doesn't variate all across the space-time, all the manifold. But if it's non-zero, then the interpretation of this is a percentage deviation from perfect homogeneity. So percentage deviations from its mean value. And this is something that we can use in quantum gravity, because we can just simply plug in this observable H relative, which is this homogeneity observable inside the path integral. And in causal dynamical triangulations, we have a well-defined way of doing this, which is just introducing this quantity inside the sum over all possible discretizations of spacetime. Now, the expectation value that we get of this observable is the homogeneity of this emergent universe that comes out of the path integral. And this is exactly what we were looking for, a way of testing the homogeneity and the isotropy of the emergent universe that comes out of this nonperturbative path integral, this the zeta-like universe. And this can be evaluated using Monte Carlo simulations, as Renate explained before. Now, I'm going to show you just a simple application to a toy model, because there are many technicalities in higher dimensions, but this observable is well defined in any dimension D of spacetime. Now, as Renate showed you before, these two-dimensional quantum geometries, they have a really weird shape, and which is an example. This is just an example of the path integral configurations, but one can still apply these observables. One knows how to measure distances in these quantum geometries, which is just the link distance between one point and another. And one can also measure the volumes and the size of these geodesic spheres, which is counting the number of building blocks inside. So again, if you zoom in, you can just construct a geodesic sphere around a point. One can coarse grain a property. This property can be, for example, the scalar curvature at each of these points. One coarse grain this property, and if one wants to know if the spacetime is homogeneous, one just applies the observable that we defined before, which is measure the variance of the coarse grain property all across the manifold, which is basically comparing the coarse grain property in different geodesic spheres inside this spacetime. And well, we did this for several properties. This is just an example of the results for the scalar curvature at a point, or its discretized form, the regular discretized form of the scalar curvature in these implicit manifolds. So in this plot, in the vertical axis, you see the value of the inhomogeneity observable. Remember that its interpretation was the value of this was a percentage deviation from perfect homogeneity. So in this case, at very short scales delta, which is, remember, the size of these chunks of the universe, at very short scales, we have 100% size inhomogenities. This means that the fluctuations of this curvature are of the size of the mean value. But if one starts coarse graining more and more and more, which is basically taking geodesic spheres every time larger, then inhomogenities are kind of disappearing. So the spacetime starts looking every time more homogeneous. And this goes with the intuition that if you start looking at a space with every time more blurry vision with less resolution, then everything will look more homogeneous. And one can take suitably a continuum limit of this, because this is what we are interested in, by just analyzing how this measure scales when one scales the size of the universe. One suitably rescales this delta, this size of the chunks of the universe, and one can take the continuum limit with this rescaling. If we do this, at least in this toy model of 2 dimensions, we get that in the continuum limit of these 2-dimensional geometries, we have 20% size inhomogeneity. So the curvature fluctuates with fluctuations around the 20% of the mean value, which is kind of large. Again, this is just a toy model to apply and see the properties of these observables, but the main goal is to apply these into 4 dimensions. Now, I don't know how much time I have. 3 minutes. Then I will briefly sketch what we do with isotropy. Isotropy is a bit more complicated because to define isotropy, one needs to test spherical symmetry of a property. And we're also doing this without any rotation group. We only have distances and volumes. No, so what we do to bypass the use of this rotation group is to define an isotropic space as a space that at each point looks spherically symmetric. And we test spherical symmetry by defining a sphere around every point. And we measure the homogeneity of the properties on a sphere on the surface of these spheres. So at each point, we build these spheres. We coarse grain a property in the surface of these spheres, and we apply the homogeneity measure on this surface. So if around the surface the shell looks homogeneous, and we define it as spherically symmetric. And this introduces two scales. One is a scale, the radius of this sphere, and another scale, which is the radius of these chunks of the surface of the sphere. So we have a double scale dependent observable now, which basically measures the variance of a property on the surface of geodesic spheres. And one can, of course, apply this again to 2 dimensions. We get a 2-dimensional observable, which one is the size of these spheres used to test spherical symmetry, and another one is a scale that we call the angular resolution, which is the size of the chunks of these of the surface of these spheres. And if one goes towards larger scales, which is larger spheres and more coarse graining, one gets something that is every time more isotropic. In 2 dimensions, we get 1% anisotropies in a continuum limit. So to conclude very quickly, we defined quantum gravitational observables capable of determining percentage deviations from perfect homogeneity and isotropy of spacetime only using distances and volumes. These observables are also scale dependent, so we can test these symmetries at different scales. We implemented them in 2 dimensions just to study its properties and to use in a very easy way, because this is our toy model, and we obtained very promising results. And we will apply these observables and test them into 4-dimensional causal dynamical triangulations in the near future. I said this in the future because I'm really bad at coding, so I'm still implementing my 4-dimensional simulations. And this is why you didn't see any results of this yet. But a positive outcome of this implementation in 4-dimension would be that this emergent universe, this acetylike universe that appears in causal dynamical triangulations, satisfies and is compatible with the usual initially assumed initially assumed conditions for the universe for inflation to happen, which is there are upper bounds in inhomogenities and anisotropies in this initial condition, and we would like to see if our emergent universe satisfies those. So thank you very much for your time and for your attention, and I hope you liked it. Okay, we have time for 1 or 2 questions. Oh, there is one question on the second. Oh, sorry, behind. Thank you.
No, I wanted to ask you, but the emergence of these the Sitter-like properties in this Planckian spacetimes, you haven't put any cosmological constant or anything like that on the original path integral, right?
There is a parameter that can be mapped to the cosmological constant. Yes, in the bare action there is.
And the value that we find of the cosmological constant
is positive.
Is related directly with the parameter that you put in the action.
Yeah, it is. Yes, it is. So maybe I can go to the beginning. But this bare action that we use here, this discretized form, now this K4 is related to the cosmological constant. It has a functional relation with the cosmological constant in the Einstein-Hilbert action. It's particular form, but I can later show it to you. I don't have it in the slides.
One more question? No? Okay. Let us then. Oh, there is one question. Yes.
So indeed, I wanted to ask this question in her talk, but I can ask here. So what happens if you include matter degrees of freedom?
Well, that's
so in the formulation.
Yeah.
Because my motivation is so near Planck scale. So in the curvature it may be very high, and then in the high curvature scale. And the quantum fluctuation of matter degrees of freedom should have non-trivial contribution, right? So I think our dynamics are including matter may influence your formulation strongly. This is
well,
my guess.
This has been studied in 4 dimensions, and people has included scalar fields in 4-dimensional causal dynamical triangulations, and so far there is no signs that this makes a lot of difference into the emergent spacetimes. Even if one fine-tunes the parameters of these scalar fields, nothing really changes the outcome of these formulations, except if one fixes some very particular boundary conditions of these scalar fields. One can sometimes induce phase transitions in these quantum geometries, but in a regular case, there doesn't seem to be many changes in this formulation if one includes matter fields.
Thank you.
You're welcome.